still here, and then you have the machines there, and there is a latency through USC wireless or whatever connection it is, right? And then you start seeing lag in the game. You find that the people, the clients are not responding properly. Sometimes the game even crashes, you know, because you've been expecting that timing of receiving of data, right? So data packing is very, very important, and it can get really, really, really tricky at times. And one of the things which people like me, we used to do at the end of the game is to start profiling all this stuff. As a part of our debugging mechanism, I actually built in the entire network, how much data is being sent inside the theater files, so that you can go back, watch an entire game, and see where each and every, what increases the size of the packet, you know. So that can be interesting. And so at that time, bitwise operators are your best friend, because you can do a simple XOR operation to see if anything has changed within a buffer, right? And you can do a lot of different things. And at the same time, like floating values are generally the most tricky things because they keep changing, right? So what we generally do is that we'll round off the float as an int. So if we have a data of say 1.05, right? Like, and we care only about the 2 decimal places, what we'll do is we'll multiply it by 100 and then treat it as 105 and then pack the data in an efficient way, so that you don't go into all these rounding errors with respect to sending it over the network. And sometimes, yes, these rounding of values really are not good at times, but then we treat it as a mechanism for the client to handle that, you know. So we are okay with a little bit of variations. That's the reason why, like, if you play Call of Duty, for example, like if you move really, really slow, you will find the player will actually pop 1 unit, you know, just because of the fact that, just because of the rounding errors, you know. And then there are a whole bunch of compressions which you can use. Delta compression is generally the most common mechanism. So that means when you freshly join, I'm going to send you an uncompressed data, and then after that, I'm going to send a delta from whichever snap packet you acknowledged. So that would mean I'll have a delta number, and I'll say, okay, from this, because the packets can be ordered in any way. So you need to have a packet number, a packet acknowledged number, and then you say, okay, this is the new packet, the packet number is so and so. Now, from which packet is this delta from? And that is the way delta mechanism works. And then the client will say, oh yeah, I got this packet, and this is delta from a snapshot which is like, say, a second ago, and then I'm going to use that delta for actually building my my new state. And then the server sometimes can use Huffman compression. That kind of helps at times. We kind of found that as we added more and more data, and especially when there is more fluctuation, it doesn't really work that well. And the big problem is that it needs training, right? So that kind of makes it you know, a tricky thing whether to use it or not. The other interesting compression is Zlib compression, but then the problem is that it's very computationally expensive. So if you are planning to do a Zlib compression every frame, that means your server is already going to slow down just because of that, you know. But it can be used. Maybe next gen for now you can use, you know, and as your data gets larger, then you'll bump into the same problems. And then I think the Halo engine kind of uses something called a selective update system. So that means it won't send every data in the world at once. What it will do is, you are in point X, Y. Here, let me first update everything which is closer to you so that you can see it, and then let me update the other ones in a slow fashion because it doesn't matter, you know. And with respect to data packing, that's where, like, it's very important to determine what all you want to send. So for example, a lot of this stuff we kind of do it client side, and it has its own problems just because of the fact that we have like, for example, the napalm strike in Black Ops 1. People will always complain like, oh, I died, but then I see that there is no flame effect there, right? The flame effect is done on the client side, but then the killing is done by the server, right? So there will be times where things like that, you will find a discrepancy, and that could cause bad things in the game, you know. So you need to be very careful on determining what to send and what not to send. So for example, if you fire a bullet and the decals which show on the walls and stuff, they are all client side, because it doesn't matter whether the server knows that or not, because it's not important for the game, you know. So there are things like that. So if you actually fire a bullet in a wall as a client, the other guy who is in the same game might not see it in the same spot, might not see the same effect, you know. But it doesn't determine anything with the logic of the game, and that's what is important. And the best practice in data transfer, even with delta compression, is that the bad thing is new data is expensive. So if you have something fresh, completely new, that is going to be expensive, because you need to inform the client about all the states. Lots of new data is more expensive, and then the data that changes a lot is super duper expensive. So for example, if say like you do a particular action and it plays like a vision set for you, right? And then the vision set like say someone threw a grenade, right? So you need to play a vision set on you, and that vision set needs to stay there for like 3 seconds, right? So the simplest way to send that thing is like every time the time changes, I say like, oh, you have 2.5 seconds left, you have 2.4 seconds left, you have 2.3 seconds left, and you keep sending that in every snapshot, right? The other way to do is to say the duration of it is 3 seconds, here, boom, and then the client gets it as 3 seconds, and then the client automatically just lerps it over the 3 seconds. That means the server doesn't need to send that time update all the time, and that will save how many of a bits, right? And similarly, like there are times where, for example, like say when we had this issue with spawning zombies, right? If you spawn too many zombies, like you go to a particular spot and you spawn like 15 zombies, what happens is that if you spawn all the 15 zombies in one frame, right? What will happen is you need to update 15 different entities and then send all the 15. So, but what some of the people did was that they kind of selectively spawn zombies over a course of a second, right? So they'll spawn like 4 zombies, and then another 4, another 4, and then another 3, right? And what that will do is that it will reduce the amount of changes which happen in one frame, so that you can kind of spread the changes across. So that's what they did with spreading large data over time. And then you should always like try to minimize the kind of changes which you can. How do you represent that there is no change, right? So one of the simple things which we generally do is that we write a bit 0. So we'll write a bit 0 if there is no change, and then a bit 1 and then the change, right? So what that would do if there is a value which does not change at all, the cost of it is just 1 bit, and even that 1 bit over compression as a packet will just reduce to nothing, you know. So you will have to find ways to minimize indication of change, you know. And then debugging is probably the most difficult thing for a network game. It can get really tricky just because of the fact that you don't know whether it's a server or whether it's a client, and even if it's a client, sometimes one of the biggest problems for us would be that you put a breakpoint and you look into it to debug, and then suddenly you release the breakpoint and things timed out. You know, that's the most common thing which happens, and it is annoying at times. So we have systems where it will just wait if it's a debug build to ensure that it doesn't time out the client that easily. But at the same time, like the biggest savior is generally printfs. You know, as silly as it can sound, you know, the old school printf is probably the biggest savior with respect to network debugging, because especially for data which is pumped every frame, you cannot afford to like step through just like some graphics code or anything, you know. And at the same time, there are packet capture tools like wireshark, which is free, which you can use to actually understand the flow of traffic this was used when there was a interest, I primarily used it to kind of analyze how much data I was sending to our backend for all the replay files. But then we need to make sure that the sending of that data doesn't affect the game, doesn't affect the performance of the game. So that was there, and then sometimes what we do is we pad the data. So we will randomly add like ints of like 255, 255, or like 10 or 20 or whatever, some random number in between. We'll write a byte, so that in read we will again see if we can read the same byte at the same time, and that's very useful in helping you determine offsets, because sometimes what happens, and someone like me bumps into that a lot more, is that someone might change something with the game logic to read, say, 4 more bytes somewhere, and then the theater system would never be updated with that. So what would happen is that the theater files will not have that 4 bytes, but then it will read some other offset memory and it will screw it up. So it's padding some of the data to catch write and read mismatches is actually very useful to do. And then there are a lot of different tools for network emulation. So you can always run the game on an emulated network so that you can see what would be the impact of, like, say, 5% packet loss or like 200 millisecond latency or whatever. And then, so coming back to our client server thing, right? So the server is authoritative, which we figured out. So that would mean I'm going to say I'm walking 4 steps, right? And then the server decides, okay, you walk 4 steps. And what that would mean, if the server is governing all this stuff, is that your game will be much slower, right? So every time I take a step, I need to wait for the server to actually acknowledge and say, okay, you moved. And this was the problem with the original Quake. When it was initially networked, right? It was one of the early network games. And then what happened was, Carmack kind of created this mechanism called client prediction. So what that would do is that the client will still move the 4 steps, but then the server determines where you are. So if there is a mismatch, or so they look for a small rounded value. And then if there is a mismatch, then you are going to the absolute what server thought. Otherwise, you are still continuing, right? And what that would mean is that you don't need to wait every step for the server to determine where you have moved. And that kind of helps in the regular smoothness of the game, because you don't need to wait for the server to tell some of the simple things, right? And it removes like latency issues. But then, the source engine at that time, implemented that and still found one problem, right? Which would be like, okay, the server, since it's UDP, you took 4 steps, but then in your second step, the server told that you are not in position 100,0, you are in position 120,0, right? So what that would mean is that you don't want to have the pop from your 4th step to the corrected second step, right? So what the people in the source engine did was that they made sure that the client maintained a buffer of all the inputs and what were the older frames, at least to a decent level, And then if the server corrected step 2, then they will rewind to step 2 and then apply all the inputs on the client, so that it can correct it. So it's generally called the rewind and replay, And that is the most common thing which people complain in Call of Duty, called the anti-lag. Oh, anti-lag sucks, That's the famous term, anti-lag. And anti-lag is nothing but the server correcting the position or some parameter of a player, and then the client says, okay, the server told that I was wrong in step 2, let me now smoothen it to step 4 from there, so that it can correct itself. Otherwise the server has to correct it every time, So That's called client prediction. And client prediction is actually as simple as it sounds. It's actually a very complex thing. But even when it is complex, like even if you write the best and most efficient client prediction system, based on the latency, you will still have the same issue. You will still find lag. So anti-lag, even though it's called anti-lag, it doesn't really fix the lag. It kind of helps in not showing lag in a really, really bad way. So that means we go to our favorite topic, right? Lag. And so every time I suck at gaming, there's lag, right? Because I don't want to say that I'm a bad player.
Yeah, that's it.
So what are the kind of lags which you can see, right? One of the things which you experience in general is the internet lag, right? Sometimes you have to wait for YouTube to buffer its data, or like it doesn't work, let's just press F5 and refresh the page, right? The regular internet lag. I don't want to focus much about internet because it's obvious. Game-related lag. So there are different lags, and this is something which a lot of people generally don't know, who are general gamers, right? Is that they'll say, oh shit, the game sucks because it lags. And the lag is a very, very common term, but it doesn't ever determine what kind of lag it is. You know, whether it's your internet which sucks, or it's any of the game logic, right? So there's something called input lag. So the time you press the controller, a button in the controller, how much time does it take for the game to actually respond to the controller, right? And that particular section can have a lag. So, for example, I don't know, I can't